In this presentation, we introduced Densac 2.0, an upgraded optical tactile sensor designed for shape reconstruction and force sensing. Dexterous tasks in robotic applications significantly impact human welfare and demand high-resolution calibrated shape reconstruction and force sensing. Optical-based sensors offer high-resolution and valuable information for enhancing dexterity in multiple manipulation tasks. These tasks necessitate high-resolution shape reconstruction and force sensing for the fingertip. Our project's objective is to develop a tactile sensor capable of reconstructing an object's shape or estimating force for dexterous tasks. Our contributions include designing a new sensor while calibrating high-resolution shape reconstruction and six-axis French estimation and demonstrating the efficacy of transfer learning for efficient training of future sensors. Densac 2.0 is more compact and less expensive than its predecessor, Densac 1.0. The modular design enables easy replacement of damaged components. Here is an exploded view of DenseTact 2.0. Densac 2.0 comprises a camera module, LED part, gel mount, and gel with a randomized pattern covered by reflective surface. We increase the number of LED lights from 3 to 9, allowing for more uniform light distribution and resistance to external light sources. The 3D printed gel mount reflects lights to the gel through a mirror-coated surface. The top right image shows the inside of the sensor with LED illumination on the mirror-coated surface. The gel softness has been increased to 49.7 Shore 00 hardness. The randomized pattern helps extract more features from a single image. To create the unique pattern, we employed the Voronoi stippling technique to distribute points on a 2D planar surface and randomly connect them. We solved the traveling salesman problem to connect a finite set of points with known positions. The connected points were then converted into an image file, and the unique pattern was extracted using 8,192 points on a stamp. The reflective surface was made more time efficient by dipping the gel into a silicone ink mixture while holding it with a suction cup. The sensor's modular design consists of 3 parts: camera module, LED module, and gel module, all of which can be easily disassembled. For shape reconstruction, datasets were collected using a CNC machine. To account for the silicone gel's incompressible and hyperelastic properties, deformation-induced bulging in non-contact regions was considered in the generated contact shape STL file. Force datasets were collected by randomly pushing the gel with a panda arm and attaching objects to the gripper. Images from the sensor and corresponding six-axis wrenches from an ATI gamma sensor were collected simultaneously within specified force or torque ranges. The Densac algorithm features encoder and decoder components, converting a 640 by 640 RGB image input into a one-channel depth image for shape reconstruction. 2 different models were developed for encoder and decoder components, one using DenseNet as an encoder with a simple decoder model, and another using a Swin transformer-based encoder and new CRF decoder model. Force estimation models consist of an encoder component with a fully connected layer outputting a 6-axis wrench. We developed 2 transfer learning models, one 6-dimensional model taking both deflected and undeflected images as input, and a 3-dimensional model using only deflected images. These models were applied to both shape estimation and force estimation. We created 3D point clouds of the sensor surface from corresponding depth images and estimated the force from these images. The results of the sensor are displayed in the following manner. The first column demonstrates shape estimation using a Swin transformer and new CRF as the encoder and decoder. The next 2 columns show results using DenseNet with a simple decoder and 2 different sensors. The last 2 columns display force and torque estimation results from another sensor, with orange representing ground truth and blue indicating predicted force and torque values. Violin plots illustrate shape reconstruction for both models from training and test datasets. The error of DenseNet model was 0.36 millimeters, while the error from the model with Swin transformer is 0.48 millimeters. The next violin plots show force estimation for both models in training or test datasets. Both models are showing the error within 0.43 newtons. The next violin plots show torque estimation for both models in training or test datasets. In conclusion, the DenseNet model outperforms the Swin transformer model for shape, force, and torque estimation. We demonstrated that a pre-trained model from a different sensor can effectively estimate new sensory input using only about 12% of the original dataset through transfer learning. The final video displays real-time estimation of force and shape on the sensor surface. Thank you.